So here they're just asking for writing the KSB expression. In chapters 16 and 17, um, all the concentrations were to the first power. But now we're in chapter 18, we're going to have squared concentrations. So the KSP for silver sulfate is going to be the concentration of Ag plus at equilibrium squared times the concentration of sulfate. Silver sulfate is a solid, so activity is 1. And so it would just be the product of these concentrations with silver squared. For this radium iodate, the iodate would be squared. This is going to give a different kind of solubility expression when we have something like this. This is 4s cubed, versus s squared, like silver chloride would just be s squared. And so KSP is equal to 4s cubed. Here it would be the same, 4s cubed. It would be 2 squared and then s squared times s. Here, the nickel phosphate, this is nickel 2 phosphate, 3 nickels, 2 phosphates. So the nickel concentration would be cubed, phosphate squared. So this would be a bit more complex. And then we have this plutonium oxide, cation, and carbonate anion here. Write solubility equilibrium equations. So when we write the equation, it's always the same. We start off with a solid. So this would be solid iron 3 hydroxide, FeOH3 solid, going to 1 iron 3 and 3 hydroxides. So the KSP expression is always written the same way, whether it's precipitation or dissolution. And so we can figure it out. This is 1 to 1. This is a 1 to 2 ratio. This is a 2 to 3 ratio here for lead to arsenate. Okay, then we go on. The following KSP values are found in the handbook. So when we look at silver chloride, it's 10 to the minus 10. It's pretty small. It's not the smallest. 10 to the minus 50 something was the smallest. But it's not very soluble, silver chloride. On the more soluble end of the spectrum, we have some of the lead salts. And so this is 858. Let's see if I can remember that. So at the less soluble, we had 10 to the minus 50. What are some of the more soluble, insoluble salts? There are things that are way more soluble than this, but we aren't going to do the calculations because they're just too soluble. And so as far as the insoluble salts go, lithium carbonate, we say group 1, all group 1 salts are soluble, but this one isn't so soluble, like 2.5 times 10 to the minus 2. But we don't want to memorize. A lot of these lithium salts are exceptions because we say group 1 salts are all soluble, but there are more exceptions with lithium here, 3 of them right here. Lithium carbonate, lithium fluoride, and lithium phosphate. Why is lithium showing more exceptions than sodium? I don't see any sodium salts here.
Higher charge density?
Yeah, higher charge density, smaller size. And then it's pairing with high charged anions. Carbonate's -2, phosphate's a -3, and fluoride, even though it's a -1, has high charge density because of its size. Fluoride's quite small in size. And so you can see with the phosphate at the -3, it's a lot less soluble because of the stronger electrical.
Is the reason that lithium salts are just not as common because of the charge density of lithium?
Yeah, charge density of lithium. There could be other reasons as well. A lot of the elements, it goes down to things like the abundance, the stability, one, of the particular isotopes, and two, the synthesis. They say the elements were synthesized during nucleosynthesis. And those processes will distribute a lot of the elements. So a lot of the elements could have been burned off, during the nucleosynthesis, like hydrogen. Although there's lots of hydrogen in the form of water on Earth. Lithium is present in the ocean, so people are thinking about mining seawater to get lithium for batteries. but there's definitely a lithium shortage. And so there's a lithium mine in Nevada, and they use tremendous amounts of water to process the lithium and to mine it. And so it's a huge, and also in Chile and other countries where a tremendous amount of fresh water is required for mining lithium. And so it's not so environmental, these electric vehicles. And it's going to get worse as the resources become more scarce. So this is why some, it's a good idea not to put all your, eggs in one basket. That is, not to force everybody to go electric one time. I have electric. I like electric. But sometimes, you go to the charger and it's crowded and there's 3 people waiting. And each charge takes and for some people over an hour. So I'm looking at how many hours. It would be nice to know how many hours I have to wait. I waited 45 minutes and gave up and left at that charging station. But anyway, here, this is pretty soluble, but we expect lithium salts to be pretty soluble nonetheless. If we go to lead, a lot of these lead salts, well, like lead iodide's not that. 10 to the minus 9 is not that soluble. But if we go to lead chloride, it's 10 to the minus 5. That's getting pretty soluble. Lead bromide, lead 2 bromide, 10 to the minus 5. It's getting quite a bit more soluble. So these, we have to watch out for. Quite a bit dissolving. So when you wash, let's say if you wash your lead chloride with water, you're going to dissolve a lot of it in solution. We can do a calculation to see how much. There are other factors, though, that impact solubility, and that's due to the bonding. If we treated everything as being purely electrostatic point charges, like in physics, you do that. Like if you have a -2 ion, you treat it as 1 point in space with a -2 charge. And then you look at the distance between the point charges. Then it doesn't accurately correlate with the data. In other words, when we look at correlations, we typically look at R-squared values. You guys are familiar with R-squared values? Yeah, correlations. What's a perfect correlation? 1, yeah. And so the correlations aren't that great, and so we have to look at other types of bonding. And so with the sulfides, there's some significant covalent interaction, especially with the heavy metals. And so like silver sulfide, there's significant covalent interaction there. And that has to do with, it's best to understand these species using the more complete theory of chemical bonding, which was what was the more complete theory of chemical bonding called? MO theory. So it's best to use MO theory for those. And when we look at MO theory, we can simplify things into certain simple patterns. Like, let's do HSAB. Do you guys remember HSAB? Not the bank?
Hard soft acid base.
Yeah, good. HSAB theory. And so this is just some patterns that are seen when we do MO theory applied to a lot of these things. And so we could look at some hard acids, soft acids, hard bases, soft bases, and see that's going to promote those things. So like heavy metals are soft. Sulfides are soft. And so the bonding interaction is quite good, at least for in HSAB or MO theory. How do we form bonds? We form bonds by LCAO. LCAO is another acronym that you should know, which stands for
Linear combination of atomic orbitals.
Linear combination of atomic orbitals. And what combinations are good? Soft, soft, hard, hard are good combinations. They make excellent bonding MOs. We have to have an excess of bonding MOs electrons in bonding MOs versus anti-bonding, and we do that thing where we calculate the bond order and that kind of stuff. But anyway, HSAD theory is also useful in predicting products of metathesis reactions as well. You know, and this would be a more comprehensive approach to predicting these types of things. So of course, for acid base, Lewis acid base, that's the primary use for this, is Lewis acid base reactions. And looking at that. And so when we understand the lattice energies of these types of things, then it make more sense. But there's multi-factors that go into this, multiple factors, and so charge and density is one of them, and that's an important one, so that's always good. But sometimes things don't quite match with charge density. All right, let's go back and take a look. What was it, 786? 748? Maybe, let's check this. 858. All right, thank you. It's short term. Actually, both my short term and long term memory are pretty bad. So, yeah, like cadmium phosphate for sure, +2, -3, electrostatic arguments. There's pretty low solubility there. It's really highly insoluble. I mean, if you think of lead-2 chloride, how many orders of magnitude is it? Now, you have to be tricky. I mean, you have to be careful. You have to be careful because solubility is not directly proportional to KSP. It's not directly proportional, and the reason it's not directly proportional is because of the way things split. And so if I compare cadmium phosphate to lead-2 chloride, it's not entirely fair comparison. And so let's do that really quick here. And so you have to be careful of solubility and KSP. So if I had lead-2 chloride, which is fairly soluble, and I'm going to do the KSP equation. The KSP equation, the dissolution equation, this is KSP. And KSP is going to be the lead concentration to the first power, and then chloride has to be squared here. And your book is not going to do that. Lead is solid, so its activity doesn't change. Just leave that. And then we're going to assume that nothing's dissolved. We always assume that nothing's dissolved, even if it already has dissolved. We'll reset it if that's the case. And then we're going to let it dissolve. So we're going to get plus S molar here, but over here we're going to get twice as much chloride. And so this is going to be plus 2S molar. Now S is going to be the same as PbCl2. So the moles of lead that dissolve is equivalent to the moles of lead-2 chloride that dissolve because they're in a 1-to-1 ratio. However, the moles of chloride that dissolve isn't. Moles of chloride that dissolve is going to be twice as much as the lead-2 chloride that dissolved. So that's twice the solubility. And so this comes out to S and 2S. And so when we look at this, this is going to be S times 2S quantity squared, which is going to give us 4S cubed. And therefore, if I want to relate the solubility with the KSP, it's going to be the KSP divided by 4, and then we take the cube root. And so it's going to be 1/3 the KSP. And so it would be 5/3, 10 to the minus 5 divided by 3. Now, if we compare that to cadmium phosphate, that's 10 to the minus 33. So let's go ahead and look. This is going to give us 3 cadmiums plus 2 phosphates. You could skip the ice table if you want as well, but I normally do it because it's in the habit of doing. Let's see. Here, we're gonna have plus 3s molar. And so, you know, the molarity of the cadmium at equilibrium is gonna be 3 times the solubility of cadmium phosphate, because for every mole of cadmium phosphate, I'm gonna form 3 moles of cadmium. And for phosphate, it's going to be double the solubility. And so at the end of this, I'll have 3 times the solubility for the molarity of cadmium and 2 times the solubility for the molarity of phosphate. And then the KSP is equal to the cadmium concentration times squared and the phosphate concentration. Actually, cadmium should be cubed. Sorry. Phosphate should be squared. So this is going to be 3s quantity cubed, 2s quantity squared. And so 3 cubed would be 27s cubed and 4s squared. And so 4 times 27 is going to be 108 s to the 5th. So the solubility is going to equal the KSP divided by 108. And we'll just look at it in terms of order of magnitude to the 1/5. And so that was 10 to the minus 33. So 33 divided by 5, it's going to be about 6. The solubility is around 10 to the minus 6. And for this, the solubility is around 5/3. So it turns out that cadmium phosphate is still less soluble, but the solubility is not directly proportional to the KSP. You have to be careful with that. And so there are cases where the KSP is smaller, but the solubility is higher because of the way it ionizes. In this case, it wasn't like that. Calculate the aqueous solubility in moles per liter. And so here we're just going to go ahead and calculate it. I didn't bring my calculator. We could calculate the aqueous solubility here. We just plug in KSP and then solve for it. Same thing here. Plug in KSP, solve for it. So that's what these are about. Arrange the following solutes in order of increasing molar solubility in water. All right. This silver cyanide, this breaks up into 2 ions. Silver iodate breaks up into 2. Silver iodide breaks up into 2. Silver nitride breaks up into 2. So the first 4 we can compare the KSPs directly because the solubility is just the square root of the KSP. However, this one breaks up into 3. And since this one breaks up into 3, it's best to calculate the solubility. But if the numbers are huge, hugely different, then we don't necessarily have to do that. Let's approach for this. Worst case scenario is, they often say this without doing any calculations, which one, So you just do your best to estimate it. But worst case scenario is you just calculate it. And you don't have to worry about it. Which of the following saturated aqueous solutions would have the highest magnesium 2+? Well, this one is going to depend. This one's a bit trickier because for every mole of this, we get 1 mole of magnesium. For every mole of this, we get 1 mole of magnesium. For every mole of this, we get 3 moles of magnesium. And so the concentration of magnesium is equal to the solubility for A. For B, the concentration of magnesium is equal to the solubility. It's 1-to-1. However, for C, the concentration of magnesium is going to be 3 times the solubility. So we have to take the concentration of magnesium and multiply it by 3 if we're calculating it from the solubility. And so little tricks you have to watch out for. Fluoridated drinking water contains about 1 part per million fluoride. Is calcium fluoride sufficiently soluble in water to be used as a source of fluoride ion for the fluoridation of drinking water? Explain. Hint. Think of 1 ppm as signifying 1 gram of fluoride per 10 to the 6 grams of solution. And so all we have to do is we can get the molar solubility of fluoride calcium fluoride, and then the fluoride concentration should be double that. So we get 2 fluorides for every calcium fluoride. And then convert molar solubility into ppm. That's probably the easiest. And so this one we could do. I think this is the one I wanted to do, probably. Or maybe not. It sounds pretty straightforward, right? This is a dimensional analysis problem. And so here we get, again, the solubility of this, and the concentration of fluorides double the solubility, and then convert it to parts per million. In the qualitative cation analysis procedure, bismuth 3 is detected by the appearance of white precipitated bismutyl hydroxide. We used to do this in Chem 1B, bismuth. Our qualitative analysis was much more involved. But calculate the pH of a saturated aqueous solution of bismutyl hydroxide. And so this one, we just get the equilibrium concentration of hydroxide, and then it's 10 to the minus 10. And so we would assume that Kw wouldn't be significant. Kw would be 10 to the minus 14. And so I'd probably ignore Kw entirely here. Get the equilibrium concentration of hydroxide, calculate the pOH, and then calculate the pH. Pretty straightforward, would you say? Yeah. The solution is saturated magnesium palmitate, a component of the bathtub ring, at 50 degrees C. How many milligrams of magnesium palmitate will precipitate from 965 milliliters of the solution when it is cooled to 25 degrees C? So the solubility changes. You know, K changes with temperature. As K changes, so does the solubility. So we can see at 50 degrees C, it's 10 to the minus 12, 4.8. And at 25 degrees C, it's 3.3. So the solubility went down a little bit from 4.8 to 3.3. Not much. And so that means we're going to have a supersaturated solution, and therefore we have to precipitate out the excess. So in this particular problem, we'd figure out how many grams are dissolved here, and then how many grams are dissolved here in a saturated solution, and just take the difference. Okay, 10. A 725 milliliter sample of saturated aqueous solution of calcium oxalate is cooled to 13 degrees C. How many milligrams of calcium oxalate will precipitate? So, this is another problem, just the same. We calculate the solubility at one temperature, the solubility at a different temperature, and then we could figure out the difference. Here, we could figure out the difference in terms of grams, or we could figure out the difference in terms of moles, or we could figure out the difference in terms of molarity. And so if you figure out the difference in terms of molarity, then you just take the total number of liters and times it by the molarity, we get the moles, and convert that to grams. So there are different ways we could solve these here. Um, 11. A 25.00 milliliter sample of a clear saturated solution of PbI2 requires 13.3 milliliters of certain silver nitrate aqueous solution for its titration. What is the molarity of silver nitrate? So this is not an acid base, this is metathesis titration. And so what I wanted to talk, because we were just talking about titrations, I wanted to take a look at 2 different types of titrations in addition to acid-base titrations. One is this, and we just call this stoichiometry, but stoichiometry, this one's hard because when do you know the end point of the titration? How do you know what the end point of this particular titration, what it would be? What's the indicator?
it stops precipitating.
when it stops precipitating, right, when you've maxed out the precipitation. Is that easy to see? And and you're going to have to overshoot it nonetheless, so you probably track it drop by drop and then see. Doable, but not so easy to do here. But anyway, these types of problems are just variations of problems that you've probably done before. So let's take a look at this one. This one, because we often do this to measure things like, for example, there are different ways you can measure what a saturated PbI2 solution consists of. One of the ways we measure it is by seeing how many grams. If you have 25 milliliters, how many grams of PbI2 were you able to dissolve in it? That's one way. Another way is we can analyze the solution using the KSP. So if we're already given the KSP data, then this is it. So this is just going to be a stoichiometry. So we need to know how much iodide is in a saturated PbI2 solution. And so to figure that out, we'll just draw our KSP equation. Since PbI2 is a solid, I'm going to start the ice table over here, and we're just going to completely ignore that. And so we'll just say there's 0, 0, S plus 2S. And so at equilibrium, we're going to get S molar and 2S molar here. And then we see that KSP is equal to 4S cubed. And then we need the KSP value for this. And then we calculate what S is. And then we calculate what iodide is. Which is going to be 2S. And then from the iodide concentration, we'll get the silver ion concentration. And from the silver ion concentration, we'll get the silver nitrate ion concentration. And so this is just titration to determine the silver nitrate concentration here. And so this would be a metathesis style titration. The next problem is not. The next problem is a bit different. And this one would be a little bit easier to see, probably. So a 250 milliliter sample of saturated calcium oxalate requires 4.8 milliliters of 0.00134 molar KMnO4 for its titration in an acidic solution. What is the value of KSP for calcium oxalate obtained with these data? So in this case, they're not giving us the KSP. In this case, they want us to figure out what the KSP is. And the way we're going to figure out what the KSP is we're going to determine the oxalate concentration of the saturated solution. And from stoichiometry, that should just be S, because it's 1-to-1 here, calcium oxalate and calcium oxalate. In the titration reaction, oxalate is oxidized to CO2 and permanganate is reduced to Mn2+. So potassium permanganate is very common in redox titrations. There's some reasons for it. One, potassium permanganate is a very powerful oxidizer. So you can oxidize lots of different things, like oxalate. Is it possible to oxidize oxalate? What is the oxidation state of carbon in oxalate? Mm-hmm. +3. So there's not much to oxidize, not much left, but we can bring this all the way to what? +4, but we're going to need a pretty powerful oxidizer to do that. And we're going to bring it to +4 and CO2. And the pretty powerful oxidizer we're going to use is permanganate. And permanganate is going to drop down to +2. And so let's go ahead and balance these. And so we'll get 2 CO2s with 2 carbons. And that's going to give us 4 oxygens here, 4 oxygens here. And so we just need 2 electrons. And then it's balanced. Over here for permanganate, manganese is balanced, so we'll need 4 waters over here. And that will give us plus 8H plus over here. So we need 8H plus. And then this is +8 minus 1 is +7, and so we'll need +5 electrons. Which makes sense because manganese is going from what is the oxidation state of manganese over here? +7 to +2. So going from +7 to +2 is going to require 5 electrons to do that. And then what I'll do is I'm going to multiply the first equation by 5 and then combine them. And the second equation by 2. And then combine these. And so we'll have 5 oxalates plus 16H plus 2 permanganates plus 10 electrons. 10 electrons will cancel, plus 10 CO2s plus 10 electrons, which cancel, plus 2 Mn2 plus 8 H2O. Then we just check 10 carbons, 20 oxygens plus 8 is 28 oxygens, 20 plus 8 is 28 oxygens, 16 hydrogens, 2 manganese, 2 manganese. So everything's balanced atom-wise. Charge -2 plus 16 is +14. Plus 14 minus 2 is +12. So +12 on the left. On the right I have +4, so I screwed up here, I think. So the charge does not match. So let's check that again. Here, that's 5 times 2 is -10, plus 16 is +6. +6 minus 2 is +4. +4 and +4, it's balanced. All right. How you can tell the endpoint for this titration is we don't need an indicator. This is a deep purple color. This looks like very concentrated grape juice. So purple solution. Whereas this has a very faint pink color. It's almost colorless. Almost colorless. So in this titration, it's easy to see the endpoint because the purple color of the permanganate will disappear. And so what we probably should do is titrate it with the oxalate to get that to disappear. However, this is a 250 milliliter oxalate, and so they're titrating with permanganate. So what they're looking for is the color to persist. So when they're titrating with permanganate, the permanganate's purple, and then it's going to disappear as long as there's oxalate. And once all the oxalate's consumed, then the purple color persists. And so that way we can see it. Well, anyway, we have the volume and the molarity. So we have the moles of permanganate. From the moles of permanganate, then we can get the moles of oxalate. And then from the moles of oxalate, then we know that the calcium and the oxalate have to form in a 1-to-1 ratio. And that's going to, the moles of oxalate will also equal the solubility. And so this is just going to be an S squared. And so we just take S and square it. So this is another type of titration, the redox titration. And so acid-base is usually the most common type of titration we encounter. So this is kind of what I like to do. I'd like to go through all the problems, but of course we don't have time to go through all the problems. So we're going to take a look at a couple of problems here. And so the next problem we're going to look at is 26, I think. 26, okay, these are all KSP problems. Then we're going to go to the common ion effect. So let's take a look at that. And so this is just shifting the equilibrium one way or the other. (26) Assume that to be visible to the unaided eye, a precipitate must weigh more than 1 milligram. So you could get less than a milligram of precipitate, and if it's like a white precipitate, you might not even see it. You might need a magnifying glass to see it. And so if we have a milligram, then you likely see it. If you add 1.0 milliliters of 1.0 molar sodium chloride to 100 milliliters of clear saturated aqueous silver chloride solution, will you be able to see silver chloride precipitate as a result of the common ion effect? There are two ways that I do common ion. I don't know if you caught this initially when we did that. And I don't know if you wrote any notes for it. But do you remember that one problem where we expanded the volume to 3 liters? It was N02 and N2O4. And the volume was expanded. There are two ways you could have done that problem. One way is you could have done a Le Chatelier's perturbation, which I didn't do because I told you that's the long way. The same thing with this. This particular problem, the situation is it's already saturated, it's already at equilibrium. So what I could do is I could just do a Le Chatelier's type shift. That is, I say this is a clear saturated solution of silver chloride. Well, and so initially I just say, okay, nothing's dissolved, and then I'll saturate it. It's going to be S molar and S molar at equilibrium. And then I perturb it by adding more chloride. And so if I perturb this by adding more chloride, then it's going to shift left. And so what I could do is I could just recalculate it. I'll just add some more chloride here and then shift it left by doing a minus x minus x. It's no longer an S. This is Le Chatelier's. But what I like to do is I just like to reset. And so for common ion problems, or for problems where we perturb by Le Chatelier's perturbation, I just prefer to reset, like we did that one problem a while back. And so when I reset this, then I go S and S, I shift all this S backwards. If I shift all that S backwards, then what's the limiting reagent? Is there a limiting reagent? No, there's no limiting reagent. It's stoichiometric. And so I'm going to shift all the saturated solution back to 0. So I'm going to have 0 molar silver and 0 molar chloride from AgCl. And then I'm going to add the NaCl to this. The NaCl is I'm adding 1 milliliter to 100 milliliters. What do I have to do when I'm adding solutions? I have to do solution dilution because the total volume is going to be 101 milliliters. And so this is my step I I'm going to do right now. And that's going to be for sodium chloride, I'm going to have the new concentration of this, which is going to be a 1 to 101 dilution. So 1.0 to 101 dilution of 1.0 molar. And what does that come out to? .0099. Is that right? 1 divided by 101. Yeah, 0.00990. We'll only add 2 sig figs. So we'll just use that. And we're going to get 0 molar. And so we'll go with the total initial. And so this is my official initial. Now the common ion effect means that if I already have chloride here, then S, what's going to happen to the solubility? Is it going to be the same, or is it going to go down, or is it going to go up? Does solubility go down, or does solubility go up? It's going to go down, right? And so the solubility goes down. Here's this problem asking for. Okay, they're asking if we will see it precipitate. So this is getting a little bit more complicated. So KSP is equal to the silver ion concentration times the chloride ion concentration, which is going to be S times 0.0099 plus S. KSP for silver chloride is equal to, I think it was what, 1.8 times 10 to the minus 859. 820. I get this news feed. E26. 1.8 times 10 to the minus 10 here from the book. Do you think the simplifying assumption will work? Yeah, probably. Let's try it anyway. So we'll try the simplifying assumption. This is going to be S times 0.0099. So I shouldn't have deleted that. 1.8 times 10. 1.8 times 10 to the minus 10 divided by 0.0099. What does it come out to?
1.818 times 10 to the minus 8.
$1.8 times 10 to the negative 8?
Yeah.
1.81 was it?
1.818.
818. All right, repeating. Thanks. So the percent was 10 to the minus 2. Yeah. The percent change is going to be about 10 to the minus 8. So we're okay. And so the simplifying assumption didn't indeed work. All right, so that's the solubility now here. And so this is normally the way I handled it, but in this particular problem, we have to see this. They're asking us how much will precipitate out. And so normally I wouldn't calculate this over here. I just am interested in the solubility after, due to the common ion effect. But in this case, I'm going to have to do it because I need to compare it with how much was in there before. So here, we need to know what the solubility was prior to the common ion. And so I'm going to go ahead and calculate it here. And that is AgCl solid goes to Ag plus and Cl minus. Your book is going to skip this entirely and just tell you what it is. But basically, it would go 0 and 0, no common ion. These are going to be S and S. And so we're going to have S molar and S molar. And so KSP is equal to S squared, and S is just equal to the square root of KSP. So your book is going to go straight to the S is equal to the square root of KSP. And so S is equal to the square root of 1.8 times 10 to the minus 10. .8. And that gives us the solubility point quadruple 0, or 1341. Okay, so there are different ways we can do this. But this is the way we'll do it. This is 101 milliliters. And so what we can do is this. We can take the difference in the solubilities. And you could do it in different ways. Maybe this one isn't the most intuitive way. But we'll go ahead and do that. And so we'll calculate delta S. Delta S is what I had before, point quadruple 0, 1341 molar. This is the initial solubility. Minus the final solubility is going to be point, I need 7 zeros, 1, 2, 3, 4, 5, 6, 7 zeros, and a 1, 8, 1, 8. This is the final solubility. And the change in solubility is what I'm calculating here. And so let me go ahead and do that. Minus 1.818 times 10 to the minus 8. Zero point 0.000133398. That should be enough. That's a change in solubility. And so what I have is I have 0.101 liters, and I'm going to multiply it by this concentration, 13398 moles of silver chloride per liter. This is how much I lost. And then convert it to grams. Convert it to grams. I need the molar mass of silver chloride. We'll just use Wikipedia for that. And so we'll just go AgCl, since I want to save some time. 143.32. 143.32 grams per mole. And then we're going to convert it to milligrams, 1,000 milligrams per gram. So let's see what that comes out to. Times 0.101 times 143.32 times 1,000. 0.1939 grams of silver chloride precipitate. Milligrams, sorry, milligrams. Is that enough to see? No. So not visible. All right, so that's a problem of the common ion effect. Now, whether it's visible or not visible, the next section deals with what we call criteria for precipitation from solution. And so I'm not going to worry, is it visible or not? I'm just going to worry, will it precipitate or not precipitate? And we will take a look at number 30C. 31C. Okay. Will precipitation occur? So it doesn't matter if we can see it or not. We just want to know if precipitation occurs. So if we're interested, will precipitation occur or not, then what we need to see is this. We need to compare Q and K. And it's been a while since we've dealt with Q, but Q is the reaction quotient. It basically tells us, are the initial conditions, at equilibrium, too small or too big, that kind of thing. And if Q is too small, then we need more product. And we get no precipitation. If Q is equal to K, SP, then we're at equilibrium, no change at equilibrium. Now, if QSP is too big, then we have to go backwards. If we go backwards, then we get precipitation. And so basically, we're just going to compare QSP and KSP and see which of these three scenarios it is. And so we're going to just do C. One drop, 0.05 milliliters of 0.0150 molar sodium hydroxide is added to 3 liters of solution containing 2.0 milligrams of magnesium ion per liter. All right, and so the precipitate we're interested in is magnesium hydroxide, solid. And this is going to be in equilibrium of magnesium 2+ and 2 hydroxides here. And so the first thing we need is a KSP value for that. And so we've got to look that up in the book. So going to magnesium hydroxide, too far. We see a KSP value of 1.8 times 10 to the minus 11 over here. And so whenever you're given a KSP type problem, I just write the equation first and then try to fill out the table as much as possible. But here we have to do a preliminary steps. We have to do the step, the initial step, which is what? Solution dilution. And so the total volume here is going to be, this is going to kind of screw it up. And so what I'm going to do is I'm going to convert liters to milliliters. And so this is going to be 3,000.5 milliliters of total volume at the end. oh, actually, it's not even 0.5, it's 3,000.05 milliliters at the end. It's barely diluted. The water is, the magnesium, magnesium 2 plus. The sodium hydroxide is hugely diluted, so let's do the sodium hydroxide first. If we look at the dilution factor, it's 0.05, just one drop of sodium hydroxide solution into 3,000 to make a total volume of 3,000.05. And this is going to be 0.0150 molar. And so the dilution factor is huge. And so let's see what this comes out to. 0.05 divided by 3,000, 0.05 times 0.015. And it's going to come out quite small. I don't know, maybe do this in scientific. I'm going to do this in scientific notation. 2.5 times 10 to the minus 367 molar. And so it has diluted many orders of magnitude. However, the magnesium 2 plus is not going to be. Now this is 2 milligrams of magnesium 2 plus per liter. And so I'm going to convert that to molar because that's what we need for this. The dilution factor is minimal. This is a 3,000 to 3,000. In fact, this dilution factor is probably negligible. We probably could ignore it. But this is going to be 2.0 milligrams of magnesium per liter. And so let's convert that to grams. And then let's convert that to moles. And so the molar mass of magnesium is 24.31. So 1 mole, 24.31 grams. So it's a 3,000.
You have to convert the 1 liter to milliliters, since we're working with milliliters now. Of the 2.0 milligrams.
We don't, because it's per liter. If it were per milliliter, we could. I mean, the situation is this is, I don't change, like your book loves to do millimoles, milliliters, that kind of stuff. I don't change. I just always do everything molarity. And so I wouldn't change this to milliliters. I'd just leave it at liters.
How is that not going to change the calculation?
Because once I get this molarity, the dilution factor doesn't matter because the units cancel out there.
Oh, okay.
And so I don't worry about the dilution factor. I could use any units I want for the dilution factor. But as far as dimensional analysis, this is still just going to be moles per liter. Everything else is going to cancel. So I would do 3,000 divided by 3,000 divided by 3,000.05. Yeah, dilution factor is minimal. Four nines and an 8 times 2 divided by 1,000 divided by 24.31. This comes out to 8.227 times 10 to the minus 5 molar. That's it. Okay, so we know the KSP is going to equal the magnesium 2 plus times the hydroxide squared. And so the QSP is just going to be the initial concentration. So it will be the magnesium 2 plus initial times the hydroxide initial squared. And so the initial concentration of magnesium 2 plus is 8.227 times 10 to the minus 5. And the initial concentration of hydroxide is 2.5 times 10 to the minus 7. And we've got to square this. Now, You know, when we're thinking in terms of S, this is something I see all the time on tests. You know, equilibrium, I'm going to have S and 2S. So what people want to do is they want to double this. So many times people will change this from 2.5 to 5. Is that correct or incorrect? It's incorrect, right? Because S is not the concentration of hydroxide. S is the concentration of magnesium hydroxide that's dissolved. And the hydroxide is going to be double that. And so the actual solubility is half of this, 1.25. But since this is asking for the hydroxide, I'll just put it straight in there. And so let's go ahead and do that calculation. Times 2.5 times 10 to the minus 7 squared. Oh shoot, my calculator didn't do it. But the rest of this is straightforward, right? Just make a comparison. Which one's bigger?
Can you kind of talk me through again why it's not, you don't double it? Because, like, what is
okay.
S actually?
This is not the solubility. If it were the solubility, we would double it.
Okay.
This is actually the hydroxide concentration. And so this 2S is equal to the hydroxide concentration at equilibrium. Well, we already have the hydroxide concentration. If I wanted the solubility, I would have to cut the hydroxide concentration in half. And so, does that make sense?
Kind of. I don't know, it's just not really clicking for me.
Yeah, it's because it's the hydroxide. If it were S, I would double it. And so we have to keep track of these things. In the next section, we have to keep track of S versus X. And so let me talk, let's take a look at the next section, which is deal with completeness of precipitation.
So real quick, this hydroxide that we calculated with the solution dilution, is that EQ or initial?
No, that's initial. This is initial. What's going to happen here, let's go ahead and calculate what's going to happen here. I'm going to try to punch this into my phone one more time. 2.5 times 10 to the negative 7, square that, times 8.2 times 10 to the negative 5th. Gives me 5.12 times 10 to the minus 18. So in this particular case, QSP is less than KSP. Therefore, nothing happens, no precipitate forms. We need more hydroxide in there to saturate the solution. We don't have enough hydroxide. If we had too much hydroxide, then it'll precipitate. QSP will be greater, and then we'll have to reduce it. But the hydroxide is just, it's not S, it's not 2S. This hydroxide is not 2S. I'd be wrong to call this hydroxide 2S. Why?
Is it because we want to calculate Q, which is like the initial, and the initial we get from the solution dilution, but that ice table is for equilibrium?
Right, this ice table is for saturated. This is not a saturated solution. The only time 2S is equal to hydroxide is when we're dealing with a saturated solution. Since we don't even have enough hydroxide, then S and hydroxide aren't related here.
And then I also kind of don't really get, like, how did you just conceptually know that, you know, if Q is less than K, no precipitate, and if it's greater, then we get precipitate?
Because of this. If Q is less than K, then the ion product is not big enough. We need more ions in the product. And if Q is equal to K, then it's just right. And if Q is greater than K, we have too much ion product here. We have to go backwards. It's got to shift to the left. Shifting to the right is dissolution, shifting to the left is precipitation. So we're only looking at what is going to cause this to shift left. And the only thing that will cause this to shift left is if we have too much here
Oh. Okay.
in the product.
So when you have this
Mhm.
this like solution, you know, with K,
Mm-hmm.
is there already precipitate in there, like a small
Yes,
amount?
right. Or it's saturated. So there could already be precipitate in here in equilibrium with this. But we can pour off the solution itself, and that would be saturated. So we don't have to have precipitate there. But
Okay.
normally when we make it, there's precipitate there because we don't want to have to measure it so carefully.
That makes more sense.
Okay. Yeah, there's more stuff to keep track of in this chapter for the ice tables. So this is why some people say this is the hardest of the ice calculations. So let's look at this next one, and then we're going to look at S and X. You know, when I reset, I don't know if you. When I reset this is still S, but there are some scenarios where it's not going to be S anymore, and so we have to keep track of that as well. Is it 8:59? So we're going to look at 35 here next. Remember doing percent reaction? So this is kind of like the same type of deal. When 200 milliliters of 0.350 molar potassium chromate are added to 200 milliliters of 0.0100 molar silver nitrate, what percentage of the silver ion is left unprecipitated? And so here we can calculate the percent precipitated, and the difference would be the percent unprecipitated, or we can calculate the percent unprecipitated directly. But anyway, whenever we mix things, we have to do the solution dilution. So let's take care of that first. So it's going to be 200 plus 200. This is going to give us 400 milliliters. And so this is just a 1 to 2 dilution, looks like. And so if we go to the potassium chromate, it'll be a 200 to 400, or 1 to 2 dilution of 0.350. So half of 350 is 175, is that correct? And this is a strong electrolyte, so it's going to be chromate. Potassium ions are going to be a spectator in this precipitation reaction. So I'll skip some steps there. And then we'll go to the silver nitrate. It's again going to be a 200 to 400 dilution of 0.0100. Chloride will be a spectator here too. I mean, not chloride, nitrate, excuse me. Nitrate will be a spectator here too. So it's just the chromate and the silver. Silver chromate's insoluble. And so the precipitate is going to be silver chromate. But when we do the precipitation, we always do the KSP equation as written here. figure out, what's going on with the precipitation. Yeah. What I do here is I do this. This is in fact, this is 0.175 molar, and this is 0.00500 molar initially. But I don't like to do a shift, Here is QSP greater than KSP. We could calculate it, but I don't even want to know. I don't care. I don't care because if I do that calculation, I'll see if a precipitate's going to happen or more is going to dissolve. Probably precipitation is going to happen because when I look at the KSP value, it's quite small. Chromate salts have pretty small KSP values. We can take a look at the KSP value here of what it is. (1.1 times 10 to the minus 12). It's pretty small. It's going to precipitate, This is going to be way too big. But I don't even bother calculating Q. I wouldn't even calculate Q mentally. You know what I would do? I don't like doing these shifts. This is going to shift left. You know what I like to do? Reset. So the first thing I'm going to do is I'm just going to reset this. And so let's go from this, the original initial, to the reset initial. So which one is the limiting reagent here? Looks like the chromate's the limiting reagent. Do you see that? And so this is going to be what I call minus y, and this will be minus 2y.
Professor, you switched the concentration.
Oh, did I? Shoot. Thanks for catching that before. You're too far into this. What's wrong with my eraser? I'll just fix it this way. So the silver is 0.00500 molar, and the chromate is 0.175 molar. So this is going to change the limiting reagent. What's the limiting reagent now? Silver. So this is going to go to 0 molar. That's my reset. And then I double this. If I double this, that's going to be 0.01. 0.01 would be, actually, right. No, I'd have to cut it in half, sorry. I need to cut this in half. So 2y is equal to 0.05, and then I'm subtracting y, which is to be half of that. And so that'll be 0.00250. 0.00250, this is going to give me 0.1725 molar. Is that all right? Okay. And so I reset it. I just prefer to do it this way because it'll clean up the algebra here. Now what I'm going to do is I'm going to go plus S plus, this is not plus S, this is plus 2S, or plus S. And so I'm going to get 2S molar and then 0.1725 plus S molar. And so this is going to equal the silver concentration squared times the chromate concentration. And so the silver concentration squared is going to be 2S quantity squared. Chromate will be 0.1725 plus S. I look at K as so small. I think the simplifying assumption is going to work. So this is going to be 4S squared times 0.1725. And therefore S is equal to what? 0.1 times 10 to the minus 12. Divided by 4. Divided by 0.1725. Equals, and then I'm going to take the square root of that. Okay. So that means actually the percent's going to be small. This is 10 to the minus 6. So the change was 10 to the minus 6. And this is 10 to the minus 1 times 10 squared, which is going to be 10 to the 5, 10 to the minus 5%, which is valid. All right, so what we have here is we can calculate this. We should do the same thing we did before. That is, we should double check our K values. So this is going to be plus 0.2345, 1262. It's going to be 0.1725, 0.1262 molar. And this is going to be double that, and so let's go ahead and times this by 2. And this is going to come out to 0.502525 molar. And then let me calculate my K. So we're going to just check K here. So I'll take my silver concentration, square that, square this, times the chromate concentration, times 0.1725, 0.1262. And I get 1.1 times 10 to the minus 12. And so that's good. Now, when I do the percent reaction or percent precipitation or whatever, percent remaining, I have to do it versus the original. I cannot do it versus the reset. This would be wrong. And so the percent remaining would be, well, I have 0.0000502525 molar remaining at equilibrium. But the original was 0.00500 molar. That was my original initial times 100%. And so that's going to be 0.12345255 divided by 0.005 times 100. And so what I get is 0.0505% remains. And therefore, how much precipitated from the original? How much precipitated would be 100% minus that percent remaining? Which gives us 99.9495% of the original precipitated. The original, it doesn't make sense to do it from the reset. You know, even if we had a value here, we always have to do it from the original when we get percent reaction or percent remaining. And so this is 99.9495%. Is it possible to get 100% precipitation? Now, to get 100% precipitation, maybe we need to add more chromate. And we could. And so if we look at the amount remaining, And we look at it based on the chromate. So this is the silver ion remaining. It turns out we're going to have to add an infinite amount of chromate to make the silver ion concentration go to 0. You know, when we have a 0 here, it doesn't add up. And so 100% precipitation requires infinite chromate. Well, infinite chromate's impossible. Infinite chromate. Therefore, we have something called a complete precipitation. A complete precipitation is not 100%. Complete precipitation does not equal 100%. What does complete precipitation equal?
Saturated?
No, not saturated. The complete precipitation is just going to be 99.9%, 3 nines. If we get 99.9%, we call it close enough. And therefore, this is called complete, but it's not really complete. Does that make sense? To get 99.9% precipitation, we take 99.9% of the area under this curve. And this last little bit, this 0.1%, would take a lot of chromate to get, and it's not worth it. And so we get the bulk of it, the silver, out of there. Okay, good. All right, we're out of time, so I'm going to stop here. But we're going to see some variety in the calculations here again.